Welcome back everyone. Today I've decided to just do a little bit more in the tutorial series. We've looked at valves previously, so today I thought I would start looking at semiconductors. And I guess the first thing we should look at is what's a semiconductor and how does it actually work at the most basic level. So let's do that today. Now, if you like what I'm doing, then by all means please do like the videos. And if you'd like to see more, then hit the subscribe button and also hit the little chime indicator and it'll let you know when I've posted something new. So let's get on with it. So here we have the periodic table of elements. And the element that we are interested in today is silicon, which has an atomic number of 14. So let's take a look at the structure of silicon. So here we have a silicon atom, a nucleus in the center, and we're showing the electron bands, 2 in the first band, 8 in the second band, and in the last band we have 4 electrons. The last band is called the valence band, and what we find is those 4 electrons will form a covalent bond with 4 other silicon atoms and form a lattice structure in a silicon crystal. Okay, so here we have a representation of that silicon lattice structure, and each silicon atom we have here, we're showing the 1, 2, 3, 4 electrons in that valence band, and you'll note the silicon atom beside it, 1, 2, 3, 4, and what we're finding is these are those covalent bonds we've talked about, and this is the structure that's formed in that silicon lattice. This is a very stable structure. The electrons can't move freely from one atom to another, and a semiconductor like silicon, like this, is actually not a very good conductor at all because it's hard for electrons to move. And if we were to apply a voltage to this lattice structure, we wouldn't get much current flow as the electrons are really held quite tightly in those covalent bonds and don't want to move. So no current flow. With semiconductors, you do find that current flow will increase as the material is heated, but essentially it's a better insulator than a conductor. So how do we actually get silicon to act as a conductor? What we do is introduce some foreign materials into the actual structure to make it easier for current to flow, and that's called doping. So let's take a look at the different types of doping there is. Okay, so the first type of doping we'll look at is when we introduce some phosphorus into this lattice structure. So going back to silicon, we find we've got our 4 valence electrons that have formed bonds with the atoms next to them. But when we look at phosphorus, we find there's 1, 2, 3, 4, and now a 5th electron. And this 5th electron doesn't actually form a covalent bond with any other atoms, so it's relatively free to move. So if we were to put a battery across this lattice structure, we'd actually find that this electron, with being free to move, would actually be attracted to the positive terminal. And after it's moved out, that would actually form a hole. And this electron would be free to move into it. Maybe this one would move into the hole created by that. And this hole here could be filled by an electron from the actual battery. So as a result, we'd actually get current flow in this circuit. And because we're actually creating an excess of electrons, this is called N-type doping. So I guess you don't have to be Einstein to figure out that the other type of doping is called P-type doping, so let's take a look at that now. Okay, so in P-type doping, we actually introduce a small amount of boron. Now, again, silicon 1, 2, 3, 4 valence electrons. Now, when we look at boron, it has 1, 2, 3. So what we end up with is a hole in this covalent bond. Now, strangely enough, where electrons are a charge carrier, because they're free to move, well, holes are actually a charge carrier as well. So let's take a look at it. If we were to put a battery across this lattice structure the way it is, now this hole will tend to be filled by an electron from the negative terminal. And the electrons will tend to move through the holes because they're attracted to the positive terminal. So again, we've got a current flow in this direction, and we've turned a silicon lattice structure that was a poor conductor into a good conductor again. And this is called p-type doping because we've got a deficiency of electrons. Okay, so let's take a look now at what happens when we put them together and form a junction. Okay, so here we've joined a piece of N-type doped silicon and p-type doped silicon. So on the N-type we have free electrons, and on the p-type we have free holes. Now, an interesting thing happens when we put these two materials together. What we find is, near the junction, these electrons actually want to fill these holes. And we end up with a zone here with this side becoming slightly negative and this side becoming slightly positive, where the electrons have actually moved to fill those particular holes. And we call this the depletion zone. Okay, so now let's just simplify that representation a little bit. So we've got our N-type doped material here, and we've got our P-type doped material on this side, and in the middle we've actually got that depletion zone. So let's look at it now when we apply a battery across this junction. Now, the first case we'll look at is if we apply the positive to the N-type material and the negative to the P-type material. So what we'll find is in the N-type material, these free electrons will tend to gravitate towards the positive terminal, so pull further away from that depletion zone. And likewise, the P-type will tend to do the same thing. We'll tend to get an excess of holes up here, and the effect of that is we can't get any current flowing through this device, so effectively the current flow is blocked. Now let's look at it from the other point of view. Let's put the battery round the other way. So now we have a negative here and a positive here. Now, initially, nothing's going to happen because we've still got this depletion zone where everything's quite stable and nothing wants to move. But what we find is, as we increase this voltage, and in the case of silicon, it's around 0.7 volts, we actually find that the electrons that have moved across here and everything's nice and stable actually start being more attracted to this positive voltage from the battery, and they tend to start moving. And likewise, we get further electrons from the battery starting to flow through these holes. So we start to get a current flow of electrons through the holes to the positive terminal. So what we find is we get a current flow in this direction. So that's the basis of a diode. Basically, it blocks current flow in one direction, allows current flow in the other. In the case of silicon, we have a voltage of 0.7 volts that we have to actually get above before the current will flow, and that 0.7 volts is known as the forward bias voltage. So that's pretty much a semiconductor junction in a nutshell. So there we go, a nice quick little tutorial on semiconductors. It is a lot more complicated than that at the quantum level, and it's certainly beyond me, but I'm hoping that that gives you a bit of background into how a semiconductor actually works, and in the next video we'll take a look at transistors.